In this lecture we are going to discuss about capacitors. Okay. So the first question is, what is meant by a capacitor? Okay. So the capacitor has two isolated conductors. Okay. So the conductors, they will not have any contact between each other. They are isolated from each other. Okay. So two isolated conductors of any shape. So most often we deal with what? Parallel plate capacitor, right? So but there will be other shapes as well. So we will discuss a few shapes, right? So what will happen in a capacitor? If you take the parallel plate capacitor, if you apply a potential across it, then what will happen? The electrons which are present on one plate, this, let us say this is plate 1 and this is plate 2. Okay. So the conductors, they will have the availability of free charges, free electrons, right? So when a potential is applied, what will happen to the electrons on conductor 1? They are going to be attracted towards the positive potential. Okay. So if you consider it like a closed circuit, okay, so you can in fact take a battery as well. So here if you take a battery, positive is applied to conductor 1. Okay. So what will happen? The electrons will be attracted towards the positive side of the battery. Okay. And these electrons are again given to the other side. Okay. They travel through the battery and they will be reaching plate 2. Okay. So what will happen? Because of this, there will be an accumulation of positive charges on the first plate, right? Because electrons are moving away from the otherwise neutral plate. Okay. When electrons move away, what will be left out? Positive. So all of those electrons, where are they getting accumulated? On plate 2. Okay. So this is how the charge will be accumulated on either plates of the capacitor, and the magnitude of accumulated charge is going to be same. Here it is plus Q and here it is minus Q. Okay. So it also means that this entire capacitor, if you take the entire capacitor, it is electrically neutral. So when potential difference is applied across capacitor, or applied across the two conductors, okay, so what will happen? Charge will be accumulated on the conductors. And what will be the magnitude of charge? The magnitude of charge is going to be equal, okay, equal magnitude of charge but opposite in sign. Okay, so on one plate it is plus Q, on the other plate it is minus Q. Therefore, what can you say about the net charge on the capacitor? It is 0. So whenever there is an accumulation of charges, what will happen? An electric field is produced, right? So if this is all positive charges and this is all negative charges. Okay. So this area between this two plates, it is a dielectric medium. Okay. So often it is air. Okay. But you can place another dielectric material also. Okay. So what is going to happen in this case? There will be an electric field within the capacitor from the positive plate to the negative plate. Okay. So here you will have the electric field inside the capacitor. But you have to note one thing, the electric field will be inside the capacitor, but inside the plate, right, this plate, inside the conductor there is not going to be any electric field. Only in between the plates there is going to be electric field. Now the charge that is accumulated, if it is Q, okay, charge accumulated on one plate, on one of the plate, okay, that is Q divided by the potential applied, that is V, potential applied across the capacitor. Okay. So the ratio of this charge and the potential difference, this is given by C, which is called the capacitance. Okay. So capacitance is the ratio of Q by V, but it actually depends on the capacitor itself, the geometrical configuration of the capacitor. Okay. It will not depend on the charge and potential. So it is a constant. Okay. So it is a constant characteristic of the capacitor. It will not depend on the operating conditions. Now Q, how you can write? From the Gauss law, you can write Q as integral d bar dot ds, and d again we can write as epsilon E bar. Okay. So C you can write as epsilon integral E bar dot ds bar. This is the surface integral, divided by what is the potential? It is the line integral of the electric field. So here also we are not considering the sign, the negative sign, because we are already accounting for the negative sign. Okay, we are taking the potential in such a way that it is in the direction of the electric field. Then we don't have to consider the negative sign. Okay, so this is capacitance. So first we will discuss about the parallel plate capacitor. Okay, so what is the expression for capacitance? C. Okay. So one thing you need to know is ideal capacitor. There is something called an ideal capacitor. So what will be the characteristics of an ideal capacitor is that there will be no fringing effect. Okay, so we will see what is fringing. There is no fringing at edge of the plates. Okay. So what happens in a capacitor? If you take a capacitor like this is the conductor and this is the second conductor. So the electric field, once the charge is accumulated, the electric field will be from the, if this is positive charge and this is negative charge, then electric field will be like this. They will be parallel lines inside the capacitor. But as it goes to the edge, what is going to happen? There is going to be more lines. Okay. So it is going to come like this. Okay. So why? Because there is no more symmetry, right? Near the inside, in the middle of the plate, what happens? There is symmetry. Okay. So there will be, the electric field lines will be parallel. Okay. So because if you take the electric field at this point, okay, so then the electric field due to this charge is going to be in this direction, due to this point is going to be in this direction, and they will cancel out. The horizontal components will cancel out. So only this parallel component will be left out, right? So that will happen when you are going inside the capacitor. But as you go towards the edges, okay, so if you consider this point at the edge, what is going to happen? If you take this point here, the electric field due to this will be in this direction, and it is not countered by any other charge here. There is no charge here, right? So that is why the electric fields are not going to be parallel anymore near the edge of the plates. Okay, so that is called as the fringing. But for an ideal capacitor, what we do is we ignore, okay, fringe, or you can say, rather than there is no fringing, we can say fringing is ignored. Fringing at edge of the plates is ignored. Okay, so that is one thing. And also the plate separation is considered. See, this is the distance, right? This is the distance between the two conductors. So this separation is considered to be very small compared to the area of the plate. Okay, area and length of the plate. So this is the second point. Plate separation is considered very small compared to the dimensions of the plate. So from these two conditions we will derive the value of the capacitance. Okay. So what will be the electric field value? This is going to be just like for an infinite sheet. right? So for this capacitor, the same capacitor, if you take the x direction to be in this direction, right? So this is x and this is y. So Cartesian plane we are taking, okay? So what will be the electric field direction? It will be in the negative y axis side. And what will be the magnitude? It will be rho s by 2, which is the electric field due to a single sheet, but you have two sheets here, right? So there will be electric field from away from the positive charge, but also towards the negative plate. So there is two sheets here. So you are going to have 2 times of this value. So there is epsilon also here, right? So this is the magnitude and direction is minus a by bar, okay? So you can write E bar is equal to rho s minus rho s by epsilon a by bar, okay? And what is rho s? Where rho s is the uniform surface charge on the capacitor plates. And what will be the unit of this? It will be coulomb per meter square, okay? Next, the potential. So what will be the value of potential? If you take this as conductor 1 and this as conductor 2, okay, then the potential, if you take the negative sign, it should be in the opposite direction, right? So that means you can write as V is equal to minus of 2 to 1, right? Because 2 to 1, if you can see, this is opposite to the electric field direction. So you can write minus of 2 to 1 E bar dot dl bar, or you can also write as plus 1 to 2 E bar dot dl bar, okay? So that means if you are taking in the direction of 1 to 2, which is the direction of electric field, then you can just take a positive sign, okay? So this expression, you know E bar, right? So it is going to be, and dl bar, it is, see, if you are taking this expression from 1 to 2, okay? So dl bar will also be in the negative y direction, okay? So you are going to get integral minus rho s by epsilon a y bar dot, the differential length is dy in the direction minus a y bar, okay? Then what will be the limits? The limits are going to be 0 to d. What is d here? D is the separation between the two plates. So distance will be from 0 to d, right? So this, if you do, you are going to get rho s d by epsilon. So rho s you can further write as, rho s is nothing but the uniform surface charge density, that is charge per unit meter. So you can write in terms of the charge as q by a into d by epsilon. Then what is capacitance? We know it is the ratio of q and v, okay? So q by v you can get from this expression, okay? So what will be that expression? It is going to be epsilon a by d. So this is the value of capacitance for a parallel plate capacitor. Here what is epsilon? This is the permittivity of the dielectric present between the two plates, present in between the plates. And what is A? This is the area of each plate. And what is D? This is the distance between the two plates. Next we are going to discuss a coaxial capacitor. Okay, that means the two conductors, they are going to be coaxial. So what is meant by coaxial? There is one conductor and within this conductor there is going to be another conductor. Okay, and in between these two conductors there is going to be a dielectric medium. So if it is air, air also can be a dielectric. Okay, so it can be filled with air or some other dielectric material. Okay, so this will be more clear if you take the top view of the coaxial capacitor, right? So you are seeing from this direction. Okay, so this is the top view. So if this is the outer conductor, let's say the radius of this conductor is d, and smaller conductor radius we will take as a. Okay, so now we have to find out the capacitance between the coaxial capacitor. So this we will consider as conductor 1 and this as conductor 2. So here first we need to find out the electric field, right? Only after we find the electric field we can use the formula for potential, right? So we will first find out the electric field. So in order to find the electric field we are going to use the Gauss law. Okay, so for that what will you do? You take a Gaussian surface which is a cylinder, okay, and the radius is rho. So this is a Gaussian surface of radius rho. Okay, so what will be the enclosed Q? Q enclosed is equal to integral d bar dot ds bar, right? This is according to the Gauss law. Now what is the direction of d bar? D bar is going to be radially away from the conductor, right? And what is the surface area? Surface area is this. So if you take an elementary area, say this is ds, then what will be the unit vector normal to it? It is nothing but in the same direction, right? So this is ds bar as well as d bar. So they are both parallel. So you can just, instead of dot, you can remove the dot product. You can replace it by multiplication. Also at a particular distance d bar is going to be uniform throughout. So you can take it out. So what will you get? Final expression d into integral ds, and the integral ds is the total surface area of the Gaussian surface. So the Gaussian surface is a cylinder. So this is going to be 2 pi rho L, where L is length of coaxial capacitor. Okay, and what is D? You can get the magnitude of D as Q enclosed by 2 pi rho L. Okay, so since this is in a cylindrical shape, you can take the cylindrical coordinates. So what will be the radial direction in a cylindrical coordinate? It is going to be a rho bar, right? So d bar you can write as Q by 2 pi rho L a rho bar. Okay, so Q here is the charge that is present on one plate. Here Q is charge present on each plate. So we can assume the inner plate to be having a positive charge, so that Q enclosed is plus Q, okay, and this is minus Q. Okay, so once you know the electric flux density, you can find out the electric field. What is electric field? This is simply d bar by epsilon. So E bar is equal to Q by 2 pi epsilon rho L a rho bar. Okay, next we have to find out the potential. So the potential V is equal to minus of, so what will be the direction of electric field? This will be in the a phi direction, right? That means from conductor 1 to conductor 2. So potential we will take it as in the opposite direction. If you take, you can have negative value. So from conductor 2 to 1, E bar dot, then what will be the elementary length? It is going to be d rho a rho bar, right? That is the radial direction. So this is going to be integral 1 to 2 E bar dot d rho a rho bar. So here conductor 1 is at a distance of a, right? the radius is A. To conductor 2 has the distance is B. Okay. So A to B, Q by 2 pi epsilon rho L d rho. Okay. So instead of E bar we are substituting its value. Okay. So the final answer you are going to get, if you integrate, Q by 2 epsilon L ln B by A. From this expression you can get the capacitance, which is Q by V. This is equal to 2 pi epsilon L divided by ln B by A. This is the capacitor of the coaxial, capacitance of the coaxial capacitor. And lastly, we have a spherical capacitor. So here the conductors will be in the form of a sphere. So there will be one sphere and around it there is going to be another sphere. Okay. So this inner sphere radius is A and the outer sphere radius is B. So because it is a spherical capacitor, logic, what it is, coordinate system, what should we take logically? We should take a spherical coordinate system. Okay. So this is conductor 1 and this is conductor 2. Just like in the previous case, you are going to take a Gaussian surface like this. Okay. So it is another sphere. Okay. And what will be the distance? It will be rho. This is Gaussian sphere of radius rho. Okay. So if you take this conductor 1 to be positively charged and conductor 2 to be negatively charged, then what will be the Q enclosed? It is going to be plus Q. Okay. So plus Q is equal to integral d bar dot ds bar. So we already saw the volume distribution. It is going to be symmetrical. It is going to be in a radial direction, and ds also, this is the surface, right, surface of the cylinder. So wherever you take, the normal vector is in the radial direction. So d bar and ds bar, they are going to be in the same direction. Okay. So d integral ds. So what will be the total surface area of the sphere? Into 4 pi r square. So d is q by 4 pi r square. Okay. Then what about in vector form if you write? A r bar, simply in the radial direction. So from here you will get the electric field E bar is equal to d bar by epsilon. So q by 4 pi epsilon r square A r bar. Okay. From here you can find out the potential. Potential is equal to minus integral 2 to 1 E bar dot dl bar, or you can write 1 to 2 E bar dot, what is dl bar here? This is also in the radial direction. So you are going to take dr AR bar. Okay. So E bar, if you substitute, you are going to get conductor 1 is at a radius A. So limits will be from A to B. And here Q by 4 pi epsilon r square dr. So if you integrate and substitute the limits, you are going to get Q by 4 pi epsilon 1 by A minus 1 by B. Okay. So finally the capacitance C is equal to, this is V, right? So C is equal to Q by V is equal to 4 pi epsilon divided by 1 by A minus 1 by B. So this is the capacitance of a spherical capacitor. Next, energy stored in capacitor. So what is the energy stored in a capacitor? So whenever there is a charge accumulation, so we have already discussed what is the energy density. The energy density is given by, whenever there is an electric field E, then energy density is half epsilon E square. Then what will be the total energy? It is going to be the volume integral of the energy density. from this expression you can derive that the energy is going to be half into charge into potential. Okay, or if you can substitute in terms of instead of Q, if you substitute C into V, then you're going to get half CV square. And if you want to substitute V instead of Q, you're substituting V in terms of Q and C, then you're going to get Q square by 2C. Okay, so these expressions we often use in networks as well, right? Finally, the equivalent capacitances. So that means capacitors are, they can be placed either in series or they can be placed in parallel, right? So what is a series connection? This is a series connection. Okay, so that means the potential across them can be added together, C1, C2, C3 and so on till Cn. Okay, the charge will be same for these capacitors. The charge on each of the capacitors will be same. So here the equivalent C is, it can be found from this expression, 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on till 1 by Cn. And for a parallel configuration, so how will the parallel configuration be? So there will be capacitors connected in this manner. Okay, so we are taking n capacitors here, C1, C2, C3 and so on till Cn. So this you can add up all the capacitors, individual capacitors. C equivalent is equal to C1 plus C2 plus so on till Cn. Okay, so for parallel capacitors the charge on each of them will not be same, but the potential across them will be same.